Okay, so that was the directed Hamiltonian cycle, but the question is the undirected version of the Hamiltonian cycle just as difficult, or more difficult, or less difficult? Okay, so Hamiltonian cycle in undirected graphs. Given a undirected graph, G of VE, does G have a Hamiltonian cycle? I.e., is there a cycle that visits every vertex Um, exactly once, except, the start vertex, where that gets visited twice. All right? So, what do we do? How do we prove that this problem is in NP? Well, we went through that already, right? We went through that with the directed Hamiltonian cycle case, so I don't need to go through that again. But how should we prove that this problem is in NP hard? Well, we could do the 3 sets to undirected Hamiltonian cycle again. We could go through that whole thing, but honestly, that's a lot of work. That was a lot of work, and the good news is that we've proven HC directed is NP complete. And the important part for us, we've proven that it's NP hard. So, maybe we could have a simple proof. Maybe we could do a simple reduction to go from HC directed to Hamiltonian cycle undirected. Wouldn't that be nice? All right. So, what do we do in that case? Well, all we need to do for this is to somehow transform the directed edges into undirected edges, so that this transformation, if there's a cycle in this, then there's a cycle in the undirected version. But if there's no cycle in the directed version, then there should be no cycle in the undirected version. Okay, we got to prove it both ways, quote unquote, both ways, not both undirected to directed and directed to undirected. That's not what both ways means. Both ways means we got to show that the yes instances correspond to yes instances, and no instances correspond to no instances. All right. So how do we do that? Well, here's an idea. So given a graph G, we need to construct a undirected graph G prime such that G has a Hamiltonian path or cycle if G prime has a Hamiltonian path or cycle. All right? So how do we do that? Well, here's an idea. What if we do what we did with our graphing algorithms, and when we wanted to convert between directed and undirected cases, and what if we simply break this vertex up, into inputs and outputs? Okay, so what if we broke every vertex up into 3 vertices here? And with these 3 vertices, this implies a direction. So every directed edge, AB, or in this case AV, is replaced by an edge A out to V in. Okay? So every edge in the original graph goes from an output node to an input node. And of course, we have a bunch of edges that go from input node to main node to output node. Okay? So this is an undirected graph, right? But consider this. The fact that the edges from the original graph go from output to input, this still gives us a suggested direction, right? This still gives us a possible suggested direction. So how does this work? Well, let's go here. Let's test it out with graphs that have cycles and graphs that don't have cycles. So this is our original G, and this is our G prime. So in the original G graph, we have a cycle, right? Our cycle goes from here, here, here. Okay, so what does our G prime have? Does it have a cycle? And we see that indeed it does. Even though it's undirected, it goes this, and this. Okay, so far so good. What happens in a graph without a cycle? Well, in a graph without a cycle, we have our G and we have our G prime. In our graph without a cycle, look what happens. What's happening here is that we have the same number of edges, but in this case, the edges are pointing in such a way that it breaks the cycle. So what do we do here? We create the same three nodes, but in this case, because we have two edges going into V1, we have two edges that go from an output node to an input node. Okay? So there is a cycle, but what's the important thing? It's not a Hamiltonian cycle, right? So if we had a Hamiltonian cycle here, then we have a Hamiltonian cycle here because we visit every edge like this. But if we don't have a Hamiltonian cycle here, we don't have a Hamiltonian cycle here because a bunch of edges get left out. A bunch of nodes get left out. And therefore, it breaks the Hamiltonian cycle property. So a no instance corresponds to a no instance, and a yes instance corresponds to a yes instance. Okay? So this reduction, of course, is polynomial time because you're just adding three sets of extra components. I mean, two extra sets of vertices. So of course, this is a polynomial time. And the reduction is correct simply because you could do a multiple proofs. You could do a proof by contradiction, but you could do a direct proof, which shows that if we do not have a cycle, okay, then that means that we have edges, that go into the same node. And because we have edges that go to the same node, they go into the input version of the node, and that leaves the body and output nodes completely uncovered, that unable to exist in a Hamiltonian cycle. Because these are dangling. Okay? So that's how we could go from directed to undirected Hamiltonian cycle. And because we prove that, because we have this reduction, we show that Hamiltonian cycle directed is reducible to Hamiltonian cycle undirected. So what does this mean? It means Hamiltonian cycle undirected is at least as hard as Hamiltonian cycle directed. And we know Hamiltonian cycle directed is NP-hard. And therefore, Hamiltonian cycle undirected is also NP-hard. All right? Okay, hopefully that makes sense. I'll see you in the next one.